At Gentec-EO, we have been designing and using laser beam measurement instruments since the 70s. Our core values are partnership, accuracy, and rigor. Our aim is to work with our customers to achieve the most accurate measurements as possible. Today we are demonstrating how to deal with background noise in both laser beam diameter measurements and laser power measurements. Let's get started. In the first part of the workshop, we are dealing with laser beam diameter measurement, which is done with a laser beam profiler. So, what is laser beam profiling? It's the measurement of the spatial distribution of a laser beam's intensity. It's not a laser power measurement, and it's not absolute. You get the distribution of relative intensities. Your beam profiler will provide you with beam diameter, profile, divergence, astigmatism, ellipticity, relative position, and overall quality. And note that we won't measure m² parameters in this workshop, but we're happy to discuss it with you afterwards. Before you start any measurements, we need to make sure you have the right instrument. First, make sure your sensor is sensitive to your laser wavelength by checking on the spectral range it covers. You might need special filters or wavelength converters if you are outside the standard visible to near IR range. Then beam size. Your camera's pixels must be small enough to get a good resolution, and your beam must fit within the sensor size. Beam profilers are very sensitive, so we also need to check on your laser power and power density and avoid both extremes, saturation or damage, and low power level that implies dealing with sensor noise. The automatic exposure time feature that you have in our software covers 85% of the saturation level, which is ideal for an accurate reading. Please use our online product finder to easily calculate power density based on your expected laser parameters. That will help you select the appropriate camera and accessories. So now that you have selected your profiler, you have to tell it which beam diameter definition you want to use. If you are measuring a first-order Gaussian beam, then the recommended diameter definition is the ISO standard, or D4 sigma. For an ideal TEM00 beam, it is equal to the 1/e² value. The 4 sigma diameter is obtained through second moment calculation, including contributions from all the pixels in the active area of the sensor. It is more representative of the overall distribution of your beam than the crosshair-based definitions. Now, the drawback to the 4 sigma definition is that background noise has an effect on the measurement and it will overestimate your beam's diameter. To make the most accurate beam diameter measurements, there are 3 factors to consider, each detailed in the ISO standard. First thing to consider is minimum beam diameter. You have to make sure that there are at least 10 pixels inside your beam's diameter. And this is why most of our profilers have a specified minimum beam diameter to work with of 55 microns. Second is the region of interest that is used for the D4 sigma calculation. If it is too small, the beam lobes will be clipped and the result will be underestimated. But if it's too large, noise from the farthest pixels will overshoot the measurement result. Our software selects this area automatically for you when in D4 sigma mode. Third, background noise, which the ISO standard recommends to remove from the calculations. This noise, it makes the calculated diameter larger than the real value. So, with the background subtraction, you tell the software to treat all the background light as the baseline, our 0. So in a stable environment, whatever is then captured after that will only come from your laser. Now let's watch an example. So here is the profile of a green laser pointer. The diameter that we measure in the 4 sigma mode is about 5.8 8 millimeters by 8.7 millimeters. So we do see some noise from the ambient light by looking at the outlying area. It's shaded blue, not completely black. Alright, so let's get rid of this stray light. By going up, I will click on the subtract background button. The software is asking me to block my laser beam, which I'm doing. Alright. Then by clicking OK, it will record the 10 frames and makes an average of this noise. Unblocking my laser now. Okay. So the reading that we get now is about 2.9 millimeters by 3.1 millimeters. That's 50% of what we had in X and 36% in Y. Now, for the second part of this workshop, we will show you how to make the most accurate laser power measurement. Once again, we need the right detector for your application. Please call us. We make this selection process easy. We offer different types of technologies to help you out, each of them with different ranges in terms of measurable power, calibrated spectrum, and damage thresholds. One common point, they're easy to use. There are 6 main parameters involved in the selection of the best tool for measuring your laser with the highest accuracy and repeatability. Let's review them together. First, wavelength. Then the expected spot size at measurement. And your beam profile, by the way, whether you're dealing with a Gaussian or flat top beam, that helps to know. Then your expected minimum and maximum average power that you have. Alright, if your laser is pulse now, we also need to know about the expected minimum and maximum energy per pulse, the repetition rate you have, and pulse width. Depending on your setup, these parameters might actually be different from what the laser manufacturers provide. Beam size or power, for example, can be affected by optical components used in your setup, by aging parts, or by specific elements to your measurement environment, such as temperature or air circulation. We're happy to discuss this with you so you get the most out of your lasers. And that's the name of the game, right? To get strong measurements to quantify exactly how our lasers behave over time. So by the way, let me also share our general guidelines for getting the most accurate, repeatable, absolute laser average power measurements with a Thermopile detector. 8 steps. First, make sure the detector is used within specifications. Then start your laser and make sure it is stable before making a measurement. Use 40 to 60% of the optical aperture. Then heat up your Gentec-EO detector, block the laser beam, do the 0, then heat up your Gentec-EO detector again before measuring your average power using an averaging method. So that was for Thermopile detectors. With photodetectors, it is not necessary to do the thermal equilibrium steps, but still it is very important to do the 0 to remove stray light noise. Let's have a try with real detectors. Here we have a photodetector connected to my PC, providing a measurement of average power with our green laser. The initial power we measure is 24.5 milliwatts. Now I will block my laser beam and zero out the background. Takes a few seconds to zero each scale of the photodiode. This is because photodiodes have a very large dynamic range. Alright, now that this is done, I can turn my laser back on, and what we can see, 22.7 milliwatts, which is about 10% less than what we had before. Last but not least, this is a Thermopile detector connected to my smartphone via Bluetooth. Our green laser is warmed up, so is my detector with the around 38 milliwatts. Blocking the laser to do the 0, it's good to wait a little bit. because reaction time of a thermopile detector is longer than a photodiode. So let's wait a few seconds before pressing the 0 button. There we go. All right. Then unblocking the laser beam. And we see, using the average button, around 26 milliwatts. It was 38 milliwatts before subtracting the background. So 26 milliwatts instead of the 22.7 milliwatts we had just before in the other test with the photodiode detector. Why? This laser is battery powered and I just plugged it in for recharge, so I did expect a slightly higher output power than with the photodiode detector. There's a lot of things going on that can affect laser power at the output. Also, the noise equivalent power coming from this detector alone here, the Thermopile, not talking about the background noise from the environment, the noise equivalent power from the detector, it's 1 milliwatt with such a Thermopile. Therefore, the fast fluctuations in measurements that you saw at this low power level, and by the way, this probe is rated up to 15 watts, so that can be used for higher power applications. Alright, we hope you enjoyed this workshop and that you feel confident how to remove background noise for accurate laser beam profiling and power measurement. A straight light does affect your beam diameter and laser power measurements by making them larger and higher by error. We also explain how to remove thermal offset with thermopile detectors, so let's be precise together and contact us. And before we go on to questions, we'll be also available to talk with you guys during the lunch break today in the virtual conference room from 12 to 1. Thank you for your time. Looking forward to talk to you soon.